The ozone layer story, how we saved the atmosphere. Imagine breathing air that burns your lungs. Imagine sunlight so intense that minutes of exposure causes severe burns. Imagine a world where stepping outside without protection means risking cancer, cataracts, and immune system damage. This isn't science fiction or some distant apocalyptic future. This is what Earth could have become if we hadn't acted when we did. High above your head, 15 miles up in the stratosphere, floats an invisible shield made of a peculiar form of oxygen. It's spread so thin that if you compressed it all down to sea level pressure, it would form a layer barely thicker than a pencil. Yet this wispy veil of gas stands between us and radiation that would sterilize the planet's surface. This is the story of how we nearly destroyed that shield, how we discovered the threat just in time, and how humanity came together in one of our finest hours to save the atmosphere itself. It's a story of accidental invention, brilliant science, corporate resistance, political courage, and ultimately unprecedented global cooperation. By the time we're done, you'll understand what ozone is, why it matters more than almost anything else in our atmosphere, how we almost lost it, and how we pulled off what might be humanity's greatest environmental success story. This is the tale of the ozone layer, and it's one of the most important stories never properly told. Part 1. The Invisible Shield. What even is ozone? Before we can understand how we nearly destroyed the ozone layer, we need to understand what it is. Ozone sounds exotic, almost magical, but it's just oxygen with an extra atom. Normal oxygen, the stuff you're breathing right now, consists of 2 oxygen atoms bonded together, O2. Ozone is 3 oxygen atoms, O3. That single extra atom makes all the difference. While normal oxygen is odorless and benign, ozone has a sharp, distinctive smell, like the air after a lightning strike or near a copying machine. It's also reactive, unstable, and in many contexts, toxic. Here's the paradox. At ground level, ozone is a pollutant. It's a component of smog, irritates lungs, damages plants, and harms human health. But 15 miles up in the stratosphere, that same molecule is our salvation. Location is everything. The stratospheric ozone layer isn't a distinct, solid barrier. It's a region where ozone concentrations are higher than elsewhere in the atmosphere. Even there, ozone is remarkably sparse, just a few parts per million. If you gathered all the ozone in a vertical column of atmosphere and compressed it to sea level pressure, you'd have about 3 millimeters of pure ozone. 3 millimeters. That's it. That's all that stands between us and unfiltered solar radiation. The chemistry of protection ozone forms through a beautiful piece of atmospheric chemistry that's been happening for hundreds of millions of years. Ultraviolet radiation from the sun strikes normal oxygen molecules in the stratosphere, splitting them into individual oxygen atoms. These freed atoms then collide with other oxygen molecules, forming ozone. But ozone doesn't last forever. UV radiation also breaks ozone apart, turning it back into normal oxygen. What exists in the stratosphere is a dynamic equilibrium, ozone constantly forming and constantly breaking down, with concentrations remaining stable as long as the processes balance. This cycle does something crucial. It absorbs ultraviolet radiation. When UV light breaks apart ozone molecules, that energy gets absorbed rather than reaching Earth's surface. The ozone layer acts like a massive UV sponge, soaking up the most dangerous wavelengths before they can harm life below. There are 3 categories of UV radiation reaching Earth's atmosphere. UVA, the longest wavelength, mostly passes through and causes tanning and aging. UVB, medium wavelength, is what the ozone layer primarily absorbs. This is the radiation that causes sunburns and skin cancer. UVC, the shortest and most dangerous wavelength, gets absorbed completely by both oxygen and ozone in the upper atmosphere. Thank goodness for that. UVC would be lethal to most life. Without the ozone layer, UVB radiation reaching Earth's surface would increase by factors of hundreds or thousands. Life as we know it would be impossible. Evolution shaped itself around the protection that ozone provides. Life under the shield. For most of Earth's history, there was no ozone layer. Early Earth's atmosphere contained little oxygen, and without oxygen, there's no ozone. Life existed only in the oceans, protected by water from the sun's radiation. Then, About 2.5 billion years ago, photosynthetic bacteria began pumping oxygen into the atmosphere. This was the Great Oxidation Event, one of the most profound changes in Earth's history. As oxygen accumulated, ozone formed. For the first time, the stratosphere contained this protective shield. Only then could life colonize land. The ozone layer made terrestrial life possible. Every plant, animal, and fungus on land exists because of those 3 millimeters of ozone floating miles above our heads. Every forest, every grassland, every creature that ever walked, crawled, or flew on Earth's surface owes its existence to this invisible shield. Humans evolved under this protection. Our skin, our eyes, our immune systems, all developed in a world where the ozone layer filtered out the most dangerous radiation. We're adapted to the UV levels that reach the surface with the ozone layer intact. We're not adapted to what would reach us without it. This wasn't just abstract science. The ozone layer was infrastructure, the most important infrastructure on Earth, built by natural processes over billions of years. And in the 20th century, we nearly broke it. Part 2. The miracle molecule. An accidental invention. Our story's villain wasn't created with malicious intent. In fact, it was hailed as a miracle when it was invented, a solution to serious problems, a triumph of chemistry, a boon to humanity. In the 1920s, refrigeration was dangerous. Early refrigerators used ammonia, sulfur dioxide, or other toxic flammable gases as coolants. Leaks could kill people. Accidents happened regularly. The refrigeration industry needed something better, a coolant that was stable, non-toxic, non-flammable, and efficient. In 1928, a chemist named Thomas Migley Jr., working for General Motors, synthesized a new class of compounds, chlorofluorocarbons, or CFCs. These molecules combined chlorine, fluorine, and carbon in structures that seemed almost magical in their properties. CFCs were extraordinarily stable. They didn't react with other chemicals. They weren't toxic to breathe. They didn't burn. They were perfect for refrigeration, eventually finding their way into air conditioners, aerosol spray cans, foam production, and industrial cleaning. By the 1970s, nearly 1 million tons of CFCs were being produced annually. Migley demonstrated their safety in a famous stunt, inhaling CFC vapors and then exhaling them to extinguish a candle, showing they were neither toxic nor flammable. CFCs were considered so safe that regulations were minimal. They revolutionized cooling technology, making air conditioning affordable and enabling modern food preservation. Nobody suspected that these miracle molecules would nearly destroy the ozone layer. How could they? They were stable, inert, seemingly harmless. That stability was exactly what made them dangerous. The journey upward. Here's the problem with making a molecule too stable. It doesn't break down. Ever. CFCs released at ground level don't react with anything in the lower atmosphere. They don't dissolve in rain. They don't get absorbed by soil or plants. They just accumulate in the air, gradually mixing upward. Over years and decades, CFCs make their way into the stratosphere. It's a slow process. The stratosphere isn't easily accessible from ground level, but inexorably, these persistent molecules drift upward on atmospheric currents. Down at ground level, CFCs remain inert, but the stratosphere is different. Up there, intense UV radiation that never reaches the surface can break chemical bonds that are stable at lower altitudes. When UV light strikes a CFC molecule in the stratosphere, it tears off a chlorine atom. That chlorine atom is a chemical weapon. It attacks ozone viciously. A single chlorine atom can destroy thousands of ozone molecules before it's finally neutralized. The process is catalytic. The chlorine isn't consumed in the reaction, so it keeps destroying ozone over and over again. Think about that. We released millions of tons of these compounds at ground level, thinking they were harmless because they didn't react with anything. We didn't realize that their stability was a time bomb, ensuring they would eventually reach the stratosphere where UV radiation would transform them into ozone destroyers. The first warnings. In 1974, 2 chemists at the University of California, Irvine, published a paper that would change history. Mario Molina and F. Sherwood Rowland had been studying the atmospheric fate of CFCs, not because anyone thought there was a problem, but simply out of scientific curiosity about what happened to these persistent compounds. Their calculations showed something alarming. CFCs would eventually reach the stratosphere, be broken down by UV radiation, release chlorine, and destroy ozone on a massive scale. Their paper predicted that continued CFC emissions at current rates would deplete the ozone layer by significant amounts within decades. The reaction was swift and divided. Environmental groups sounded alarms. Some scientists immediately recognized the threat, but the chemical industry, with billions of dollars invested in CFC production and products, pushed back hard. Critics questioned the science. How could you prove that something happening slowly in the stratosphere was really caused by chemicals released at ground level? Where was the evidence of ozone depletion? The theory was based on models and chemistry. Where were the measurements showing actual harm? DuPont, the largest CFC manufacturer, argued there was no proof of danger and that banning CFCs would cause economic catastrophe. Industry groups funded studies to cast doubt. Some scientists genuinely questioned whether the threat was real or overstated. This was science confronting economic interest in real time. Molina and Rowland were warning about a threat that couldn't yet be directly measured, asking society to act on predictions rather than proof. The debate would rage for years. But beneath the controversy, the science was solid. The chemistry worked exactly as Molina and Rowland described. Chlorine did destroy ozone catalytically. CFCs did reach the stratosphere. The only question was how much damage was already occurring and how much worse it would get. Part 3. The Whole Discovery in Antarctica. In 1985, the debate ended. British scientists working at Halley Research Station in Antarctica published measurements that shocked the world. Ozone concentrations over Antarctica had dropped by more than 40% during the Antarctic spring. This wasn't gradual depletion. This was a hole, a vast region where ozone concentrations plummeted to levels never seen before. The measurements were so extreme that NASA's satellite instruments had initially dismissed them as errors. The satellites had been programmed to ignore readings that seemed impossibly low. They'd been seeing the hole for years but had automatically rejected the data as faulty. When researchers went back and looked at the raw satellite data, they confirmed the British findings. Not only did the ozone hole exist, it was enormous, larger than North America. Every Antarctic spring, ozone concentrations over the South Pole collapsed, recovering only as winter ended. The discovery changed everything. This wasn't a theoretical threat anymore. This was actual, dramatic, measurable damage happening right now. The ozone layer wasn't just thinning gradually, it was developing a massive seasonal hole that exposed the region below to UV radiation levels never experienced in human history. The ozone hole made the threat visceral and immediate. You could show pictures of it. You could measure the increased UV radiation beneath it. You could point to a map and say, "There, that's the damage we've caused." Why Antarctica? The obvious question was, why Antarctica? Why was the ozone hole forming over the South Pole rather than elsewhere? The answer involved atmospheric chemistry that nobody had predicted. Antarctica's unique conditions, extreme cold, isolated circulation patterns, and unusual cloud chemistry created a perfect storm for ozone destruction. During the Antarctic winter, temperatures in the stratosphere drop below -80 degrees Celsius. At these extreme temperatures, polar stratospheric clouds form, clouds made of ice crystals that exist only in these coldest regions. These clouds aren't like regular clouds. They're chemical reactors. Chlorine from CFCs gets trapped in forms that are relatively inactive. But on the surfaces of these polar stratospheric clouds, chemical reactions convert inactive chlorine compounds into active, ozone-destroying forms. All winter long, as Antarctica sits in darkness, these reactions prepare a massive reservoir of chlorine, waiting. Then comes spring. Sunlight returns to Antarctica, triggering the waiting chlorine. UV radiation drives the ozone destruction reactions, and with so much activated chlorine present, ozone concentrations collapse. The polar vortex, strong winds circling Antarctica, isolates this air mass, preventing ozone-rich air from mixing in. The result? A massive seasonal ozone hole appearing every Antarctic spring. As spring progresses and temperatures warm, the hole fills in. But every year the cycle repeats. Nobody had predicted this mechanism. The models had shown gradual global ozone depletion. The reality was more dramatic. Severe, localized depletion occurring through chemistry that required specific conditions to activate. Antarctica provided those conditions perfectly. This discovery was humbling. We'd thought we understood atmospheric chemistry well enough to predict what would happen. Nature showed us there were mechanisms we'd never imagined, amplifying damage beyond what models predicted. The global threat. The ozone hole over Antarctica was dramatic, but the threat was global. Measurements showed ozone depletion occurring worldwide, not just at the poles. The Arctic showed losses, though less severe than Antarctica due to warmer temperatures. Mid-latitude regions, where most humans lived, showed several % depletion and growing. Scientists projected the future based on CFC emissions continuing at current rates. The models were terrifying. Ozone depletion would accelerate, the Antarctic hole would persist longer each year and potentially appear year-round. Arctic depletion would worsen. Mid-latitude losses would increase, exposing billions of people to elevated UV radiation. The consequences would be catastrophic. Skin cancer rates would skyrocket. Millions of additional cases. Cataracts would become epidemic. Immune system suppression from UV exposure would make populations more vulnerable to disease. Crops would suffer reduced yields. Marine ecosystems would collapse as UV radiation penetrated ocean surfaces, killing plankton and disrupting food chains. Some scientists estimated that without action, ozone losses could reach 50% or more by mid-century. At that point, spending time outdoors during sunny periods would require serious protection. The world we'd taken for granted, one where you could walk outside without thinking about cosmic radiation, would be gone. This wasn't distant or uncertain. The chlorine was already in the stratosphere. Even if all CFC emissions stopped immediately, ozone depletion would continue for decades as existing chemicals worked their way upward and released their chlorine. We'd already committed to damage that would take generations to heal. The question was, would we act in time to prevent the worst outcomes, or would we wait until the damage was irreversible? Part 4. The Rescue. The Montreal Protocol. On September 16, 1987, representatives from nations around the world gathered in Montreal, Canada. They came to sign a treaty that would be hailed as humanity's most successful environmental agreement. The Montreal Protocol on substances that deplete the ozone layer. The protocol committed signatory nations to phasing out production and consumption of CFCs and other ozone-depleting substances. It set specific targets and timetables. It established mechanisms for monitoring compliance. Most remarkably, it included provisions for helping developing nations transition to alternatives. This was unprecedented. An international treaty requiring economic sacrifice based largely on scientific predictions of future harm rather than immediate crisis. Yes, the ozone hole had been discovered, but most people weren't experiencing direct effects yet. This was preventive action on a global scale. The treaty wasn't perfect initially. The first version's targets weren't aggressive enough to prevent serious damage, but the protocol included provisions for strengthening based on new scientific evidence. As measurements showed continued depletion, amendments tightened restrictions. The London Amendment in 1990, the Copenhagen Amendment in 1992, and others progressively strengthened the agreement. Eventually, the protocol mandated complete phase-out of CFCs and similar compounds. Production of CFCs for most uses ended in developed nations by 1996 and in developing nations by 2010. The world switched to alternative coolants, new propellants for aerosols, different foam-blowing agents, and substitute solvents. Why it worked. The Montreal Protocol succeeded where so many environmental agreements fail. Understanding why is instructive for other global challenges. First, the science was clear and convincing. Molina and Rowland's chemistry was solid. The ozone hole provided dramatic visual evidence. Scientists from multiple nations and institutions confirmed the findings. There was scientific consensus that couldn't be easily dismissed. Second, alternatives existed or could be developed. The chemical industry initially resisted, but companies realized they could profit from developing substitutes. DuPont, once a leading CFC producer, became a major manufacturer of replacement compounds. Economic doom predictions didn't materialize because innovation provided solutions. Third, the threat was universal. Ozone depletion affected everyone, regardless of geography or politics. There was no safe haven. Rich and poor nations alike faced increased UV radiation. This created solidarity and shared purpose. Fourth, the treaty was flexible and adaptive. Starting with achievable targets and strengthening over time allowed nations to adjust. Mechanisms for helping developing nations prevented the "we won't sacrifice while you get to develop" conflict that has paralyzed other environmental agreements. Fifth, there was political will. Leaders like Ronald Reagan and Margaret Thatcher, not typically associated with environmental advocacy, supported action. Scientists like Molina, Rowland, and many others persistently communicated the threat. Environmental groups mobilized public pressure. The combination pushed governments to act. Finally, there was a sense of urgency tempered with realism. The threat was serious enough to motivate action, but not so immediate that panic prevented thoughtful response. The damage hadn't yet become catastrophic, giving time for orderly transition. The long recovery. Signing the treaty was just the beginning. Healing the ozone layer would take decades due to the persistence of ozone-depleting chemicals in the atmosphere. CFCs can survive in the stratosphere for 50 to 100 years. Even after emissions stopped, the chemicals already released continued destroying ozone. Chlorine concentrations in the stratosphere peaked around 2000 and have been slowly declining since. The ozone hole continues to appear every Antarctic spring, though measurements show it's gradually becoming less severe. Scientists project that Antarctic ozone will return to 1980 levels, before the hole appeared, around 2070. Mid-latitude ozone should recover sooner, perhaps by 2050 or 2060. This is generational timescale recovery. Children born today will be senior citizens before the ozone layer fully heals. This underscores both the magnitude of the damage we caused and the critical importance of acting when we did. Had we waited even another decade to regulate CFCs, the damage would have been significantly worse, and recovery would take correspondingly longer. Had we never acted, well, the consequences don't bear thinking about. Unexpected victories. The Montreal Protocol had benefits beyond saving the ozone layer. Many CFCs are also powerful greenhouse gases, far more potent than carbon dioxide at trapping heat. By eliminating CFCs, the protocol has prevented significant additional global warming. Studies estimate that the Montreal Protocol has done more to mitigate climate change than any other single international agreement. It's a climate treaty that nobody calls a climate treaty, proving more effective than agreements explicitly designed to address warming. The treaty also demonstrated that international cooperation on atmospheric issues is possible. It showed that industry can adapt when given clear signals and reasonable timelines. It proved that acting on scientific predictions before catastrophe strikes can work. The Montreal Protocol is often cited as a model for addressing climate change. While the challenges differ, carbon dioxide is more fundamental to the global economy than CFCs were, and climate change is more complex than ozone depletion. The lessons remain relevant. Clear science, political will, international cooperation, and timely action can solve seemingly impossible global problems. Part 5. Lessons and Legacies. The Science That Saved Us. Mario Molina and F. Sherwood Rowland received the Nobel Prize in Chemistry in 1995, along with Paul Crutzen, who had done pioneering work on ozone chemistry. The award recognized not just their scientific achievement, but the profound impact their work had on humanity's future. Their story embodies what science at its best can do. They weren't looking for a crisis when they started studying CFCs. They were simply following curiosity about the fate of these persistent compounds. Good science, pursued for its own sake, revealed a threat nobody suspected. Their willingness to speak out despite industry opposition took courage. They faced criticism, skepticism, and professional risk. They persisted because the evidence was clear and the stakes were enormous. They communicated their findings not just in scientific journals, but to policymakers and the public. The ozone story validates the value of basic research. Nobody funded Molina and Rowland to save the world. They were doing fundamental atmospheric chemistry. The practical importance of their work only became apparent after their discoveries. This is why supporting basic science matters. You never know what critical insights might emerge. What we avoided. It's worth contemplating the alternative timeline. What would have happened without the Montreal Protocol? By now, without regulation, ozone depletion would be severe globally. The Antarctic ozone hole would persist nearly year-round. Arctic ozone would show massive springtime losses. Mid-latitude depletion would be dramatic, perhaps 30 to 50% in some regions and seasons. UV radiation at Earth's surface would be far higher. Outdoor activities during peak sun hours would be dangerous without protection. Skin cancer rates would be vastly elevated, millions of additional cases annually. Cataracts would be endemic. Immune system effects would make populations more vulnerable to infectious disease. Ecosystems would be crashing. Phytoplankton, the base of ocean food chains, would suffer massive die-offs. Coral reefs would face additional stress beyond warming and acidification. Terrestrial plants would show reduced growth and altered chemistry. Agricultural yields would decline significantly. The economic costs would be staggering. Healthcare costs from increased disease, agricultural losses, ecosystem service disruption, the need for protective measures in daily life. Some estimates suggest trillions of dollars in damage, affecting billions of people. We avoided this future because scientists discovered the threat, communicated it effectively, and the world listened and acted. This is humanity at its best, using knowledge to foresee disaster and wisdom to prevent it. The ongoing vigilance. The ozone story isn't entirely over. Scientists continue monitoring the ozone layer, tracking recovery, and watching for new threats. In recent years, measurements detected unexpected increases in one type of CFC, suggesting illegal production somewhere, probably China. The increases were small and have since been addressed, but they show the need for continued monitoring and enforcement. New chemicals require evaluation. When industry develops substitutes for ozone-depleting substances, scientists assess whether these alternatives might cause different problems. Some CFC replacements turned out to be potent greenhouse gases, leading to further regulations. The polar regions, especially Antarctica, remain sensitive indicators. The ozone hole continues appearing each spring, though gradually weakening. Any unexpected changes in its severity or duration could signal new problems or confirm recovery projections. This vigilance is the price of protection. The ozone layer won't truly be safe until chlorine levels in the stratosphere return to natural background levels, still decades away. Until then, we watch, measure, and guard against backsliding. Hope for other challenges. The ozone story offers hope for addressing climate change and other global environmental challenges. If we could solve ozone depletion, why can't we solve these other problems? The honest answer is that ozone depletion was, in some ways, easier. The chemicals causing it had substitutes. The economic disruption of banning them was manageable. The science was relatively straightforward and quick to confirm. The benefits of action were distributed similarly to the costs. Climate change is harder in every way. Fossil fuels are deeply embedded in global economy. Alternatives exist, but transition is more complex and expensive. The benefits of action accrue over longer timescales and may feel distant. Nations have widely varying contributions to the problem and capacities to address it. But the fundamental pattern holds. Identify the problem, understand the science, develop alternatives, build political will, achieve international cooperation, and act before catastrophe. It worked for ozone. The principles apply broadly, even if implementation is more challenging. The ozone story proves that humanity can make collective, precautionary decisions based on scientific evidence. We can forego short-term convenience for long-term survival. We can cooperate internationally despite competing interests. We can change course when evidence demands it. These abilities exist within us. The ozone layer's recovery is proof. Part 6. Looking up. The shield endures. Right now, 15 miles above your head, the ozone layer is doing its job. It's absorbing UV radiation, protecting life below, making the world habitable. It's been damaged, but healing. It's thinner than it was, but recovering. When you spend time outdoors on a sunny day without burning, thank the ozone layer. When you see plants growing, animals thriving, ecosystems functioning, remember the invisible shield making it possible. When you consider how different the world could be, how much worse, appreciate what we saved. The ozone layer is infrastructure that we inherited, courtesy of billions of years of evolution and photosynthesis. We nearly wrecked it through ignorance and neglect. We saved it through science, cooperation, and determination. The scientists' gift. The scientists who discovered the threat gave humanity an extraordinary gift: time. They found the problem before it became catastrophic. Their warnings came early enough that action could prevent the worst outcomes. Melina and Roland could have published their findings in obscure journals and moved on to other research. Instead, they made sure the world understood. They testified before Congress. They spoke to journalists. They engaged with policymakers. They weathered industry attacks and professional skepticism. Their persistence, and that of countless other scientists who confirmed and extended their work, saved lives beyond counting. Every person who doesn't get skin cancer because the ozone layer recovered owes a debt to these researchers. Every ecosystem that doesn't collapse under excessive UV radiation exists because scientists sounded the alarm in time. This is what science does at its best. It gives us foresight. It reveals hidden threats. It provides the knowledge needed to make wise choices. The ozone story shows why funding science, listening to scientists, and acting on evidence matters. Our responsibility. We inherited a healing ozone layer. Our responsibility is to complete the recovery and ensure we never threaten it again. This means maintaining the Montreal Protocol's provisions. No backsliding on CFC bans. Proper disposal of existing CFC-containing equipment. Continued monitoring. Enforcement against illegal production. Careful assessment of new chemicals. It means applying the lessons learned. When science reveals environmental threats, we must listen. When evidence points to human causes, we must act. When solutions require international cooperation, we must cooperate. When short-term costs are necessary for long-term survival, we must accept them. The ozone layer's recovery will be complete around 2070, depending on region. That's still half a century away. Current children will be grandparents before the job is done. Maintaining commitment across generations is challenging, but the alternative, abandoning the recovery partway through, is unthinkable. The broader view. The ozone story is part of a larger narrative about humanity's relationship with the atmosphere. For most of history, we viewed the sky as infinite, immune to human impact, unchangeable. The 20th century taught us otherwise. We learned we could alter atmospheric chemistry on global scales. We learned our local actions could have planetary consequences. We learned that what goes up might not come down, or might come down in forms we didn't intend. We learned that atmosphere, like any commons, can be degraded by unregulated use. But we also learned we could recognize these impacts, understand their causes, and take corrective action. We learned that science could guide policy. We learned that international cooperation was possible. We learned that prevention was achievable. The ozone layer's story sits between tragedy and triumph. The tragedy: we damaged something irreplaceable through carelessness. The triumph: we discovered the damage in time, understood its causes, and united globally to fix it. Conclusion: the shield we saved, from accidental invention to environmental catastrophe to unprecedented global cooperation to ongoing recovery, this has been the journey of the ozone layer story. It's a tale of human fallibility and human capability, of crisis and response, of how close we came to disaster and how we pulled back just in time. The ozone layer, that 3-millimeter thick shield floating in the stratosphere, remains one of Earth's most important features. It's been protecting life for hundreds of millions of years. 60 years ago, we didn't know we were threatening it. 50 years ago, we discovered the threat. 40 years ago, we acted. Today, it's healing. This healing will take decades more to complete. Chlorine concentrations in the stratosphere are declining, but slowly. The Antarctic ozone hole still appears every spring, though measurements show improvement. Mid-latitude ozone is recovering. The trajectory is positive, but the journey is long. Every year without a CFC emission spike is a year closer to recovery. Every measurement showing chlorine decline is confirmation we're on the right path. Every model projection of eventual healing is reason for hope. The ozone layer will recover because we chose to save it. Think about what this means. We identified a threat that most people couldn't see or feel. We understood its causes through atmospheric chemistry. We developed alternatives to harmful chemicals. We achieved unprecedented international cooperation. We're committed to a recovery that will take generations. We did this because it was necessary, because science showed us what was at stake, because we chose to act. The ozone layer's story is ultimately a story about choice. We chose to investigate CFC's atmospheric fate. We chose to take the threat seriously. We chose to regulate despite economic costs. We chose cooperation over competition. We chose the long term over the short term. We chose survival. Instead, it's becoming a story of recovery. Not fast recovery, not perfect recovery, but real recovery nonetheless. The shield we nearly destroyed is being restored, slowly but surely, by the simple act of stopping what was harming it. Look up, 15 miles straight up, in the cold, thin air of the stratosphere. Ozone molecules are right now absorbing ultraviolet radiation, protecting you, protecting life, doing what they've done for hundreds of millions of years. They're doing it in lower concentrations than they should, but more than they would without the Montreal Protocol. That protection exists because scientists did their job, politicians did their job, industry adapted, and nations cooperated. It exists because humanity, faced with a threat to our atmosphere and our future, chose to act. The ozone layer's recovery is proof that we can solve global environmental problems when we commit to doing so. It's proof that science, policy, and international cooperation can work. It's proof that prevention is possible and worthwhile. It's also a reminder that the atmosphere is fragile, that human impacts are real, and that vigilance is necessary. We saved the ozone layer, but we must remain committed to protecting it. We must apply these lessons to other atmospheric threats. We must remember that prevention is always easier than cure. The ozone layer story isn't over, but its arc is clear. From crisis to cooperation to recovery, it traces a path we can follow for other challenges. It's one of humanity's finest hours, even though that hour is stretching into decades. We saved the atmosphere. Let's make sure we keep it saved. The shield endures. The healing continues. The story goes on. And above it all, filtering sunlight, protecting life, the ozone layer does its quiet work, wounded but recovering, damaged but healing, sustained by our commitment to a choice we made in 1987, to save the invisible shield that makes life on Earth possible. That's the ozone layer story, a tale of near disaster and remarkable recovery, of science and courage, of humanity rising to meet a challenge we didn't even know existed until we'd almost lost what we'd always taken for granted. It's a story worth knowing, worth telling, and above all, worth continuing through action and vigilance for generations to come.